This is the Moser solid rocket motor. Operating on a test stand at a chamber pressure of 22.5 bar, it serves as the physical baseline for evaluating multi-phase flow simulations. At the nozzle exit, the macroscopic flow conditions are extreme. The centerline velocity reaches Mach 2.3, while the internal chamber temperature peaks at 3,325 Kelvin. Because the primary combustion is fuel-rich, the exhaust consists largely of hot hydrogen gas and carbon monoxide. As these species exit the nozzle, they contact ambient air and ignite, forming a secondary reacting shear layer. This gas mixture carries a highly concentrated dispersed phase of liquid alumina particles, representing a massive 31% mass loading relative to the gas. Supersonic expansion, non-equilibrium chemical kinetics, and an immense particle loading create a complex, hostile environment. Standard time-averaged computational models struggle to accurately resolve these overlapping physical states. The complexity increases because the solid propellant contains alkali impurities, specifically potassium and sodium. As these trace elements pass through the intense heat of the recombustion flame, they undergo rapid thermal ionization. This diagram outlines the experimental sensor array designed to capture the resulting multiphysics data, utilizing simultaneous infrared spectrometry alongside an X-band organolyzer. The ionization process generates a high concentration of free electrons. This charged field interacts with incoming electromagnetic waves, resulting in significant radio signal attenuation. For radar detection, the critical dependent variable is the pseudo-Doppler spectral broadening of the backscattered wave, measured using a UHF radar offset at a 60-degree angle.
This spectral broadening is a direct product of macroscale physical oscillations occurring within the ionized field over time. Because steady-state algorithms cannot resolve these transient oscillations, predicting the radar signature requires the high-fidelity, multi-phase implicit large eddy simulation approach. To evaluate the necessity of transient modeling, researchers established a baseline using a 2D axisymmetric RAND simulation on a 41,000-cell grid with a K-omega SST model. They contrasted this against a 3D unstructured framework run in the CDRE multiphysics code. This method relies on implicit dissipation of the numerical scheme rather than explicit subgrid turbulence models. This computational mesh visualization shows the first intermediate step, an 8.4 million cell grid structured specifically to capture the primary dynamics of the mixing layer. This massive 20 million cell grid represents the high-fidelity standard, featuring tight 0.5 mm azimuthal cells directly at the nozzle outlet. Processing this massive 20 million cell environment strictly to reach the statistical convergence of the turbulent structures requires 2 million CPU hours. Evaluating these distinct levels of spatial refinement reveals where time-averaged equations fail to capture the physical behavior of a supersonic reacting flow. The immediate aerodynamic challenge lies just outside the nozzle lip. The simulation must predict the exact spatial onset where the flow transitions into a three-dimensional shear layer. This 3D visualization displays the formation of longitudinal, Gortler-like vortical structures, predicted by the transient solvers, immediately downstream of the expansion fan. As the flow propagates rightward, these distinct longitudinal streaks physically merge. This specific interaction triggers the first major flow fluctuations in the plume.
A 2D axisymmetric RANS model smooths the velocity gradients radially, preventing these defined longitudinal vortices from forming and suppressing the mechanism of their breakdown. This initial breakdown determines the onset of chaotic mixing, which in turn establishes the location of the secondary combustion flame. This line graph compares the root mean square of fluctuating velocity. The black RANS curve shows turbulence developing artificially early, reaching a low-energy, steady state. In contrast, the green 20 million cell simulation records massive turbulent fluctuations, peaking sharply between 1 and 3 nozzle diameters downstream. This graph tracks the axial evolution of the shear layer's thickness. The RANS approach generates a strictly linear expansion. Meanwhile, the large eddy simulations produce nonlinear curves, indicating a mixing layer that remains partially laminar before structural breakdown. Grid resolution directly determines the predicted length of the potential core. Change in this length shifts the calculated position of the primary heat release zones. The physics models must also track the dispersed liquid alumina phase, which is calculated as a 3.5 micron particle distribution via the Hermsen correlation. Although the micro-level models for drag and heat flux are identical in both solvers, the resulting macro-scale dispersions show a significant divergence. Because the RANS approach relies on a time-averaged velocity field, the heavy particle spray remains tightly bound along the central axis, preventing outward expansion. The transient solvers calculate actual turbulent eddies. These physical structures catch the liquid particles and fling them outward radially into the surrounding shear layer. This outward dispersion carries thermodynamic consequences. Moving high heat capacity liquid alumina radially outward drastically raises the local temperature at the plume's external boundary. Because particle mass governs local temperature, steady-state aerodynamics produce a plume model with the wrong shape, intensity, and location for the ionizing flame. This cut plane at half a nozzle diameter downstream captures the extreme temperature gradients and thermal mixing driven by transient turbulence. To bridge the gap between these fluid dynamics and the radar signature, we must convert the transient velocity fluctuations into a power spectral density analysis. This plot displays the power spectral density of the velocity fluctuations 10 nozzle diameters downstream, deep within the fully developed turbulent zone. The energy cascade aligns with the dashed line, satisfying the Kolmogorov universal law for isotropic decay and confirming the validity of the simulation. However, there are distinct anomalies breaking from that universal law. Isolated low-frequency structural modes appear, specifically a peak near a straw Hall number of 0.45. These peaks represent massive, rhythmic flow structures within the exhaust, specifically the bulk physical flapping of the plume's tail. Moving to 20 diameters downstream, this plot confirms the persistence of those large-scale structural frequencies. While the overall turbulent kinetic energy has decayed, the 1.8 kHz structural peak remains prominent. This macroscopic fluid flapping drives the alkali chemistry. As the plume tail oscillates in space, the zones of free electrons shift physical position along with it. This rhythmic shifting of the electron cloud is the physical mechanism modulating the backscattered UHF radar signal. Standard Navier-Stokes equations omit these large-scale transient oscillations. Accurately predicting the electromagnetic cross-section depends on resolving the multi-phase, unsteady eddies that drive the highly ionized flow.